In this video, we are going to solve for a frame structure using slope-deflection equation. The frame we are interested now is single-story structure, where its height and width are both L. The top of frame is subjected to uniformly distributed load W and both legs of frame are fixed. Let's segmentize the frame element and assuming the internal end moment is rotating in positive direction, which is clockwise direction. Recalling that we have two different types of slope deflection equations, which are applicable to different span types. The first type of equation is used since all the elements are either end span with far end fixed or internal span. We can now construct moment equation with numerous unknowns. FEM in these equations can be solved using readily available formula. In this structure, FEM due to span loading is only developed in member BC, since it is the only transversely loaded member. When using the formula, we need to know that the result is expected to follow the convention it outlines. If the resultant FEM acting in opposite direction of our assumed end moment, we are bound to put a negative sign on it. When analyzing a frame, it is important to know whether the frame will sidesway. For a symmetrical frame like this that is not subjected to lateral load, we can assume sidesway does not occur. Even if it is subjected to lateral load, proper restraint against horizontal direction will prevent sidesway. Conversely, unsymmetrically configured or loaded frame will experience sidesway, as well as laterally unrestrained frame that is subjected to lateral load. The frame we are looking now is symmetrical in terms of loading, configuration, material, and support condition. Therefore, it should not experience sidesway. For this reason, we are good to eliminate unknown span and displacement delta. The boundary conditions of members govern the presence of rotation at both ends. For point A and D, they are attached to fixed support and thus we expect no rotation occurs here. On the other hand, point B and C are free from any form of restraint, and we should allow the rotation parameters theta B and theta C to be non-zero unknown. Now, let's simplify all 6 internal moment equations to ease our next course of action. With unknown theta B and theta C, we know we need to make 2 equations containing both of them to solve them. Both equations can be constructed by taking moment equilibrium at point B and C, where the sum of acting moment there should be 0. After we obtain the simultaneous equations, we will be able to solve for the unknown beam rotation. By substituting the solution into all internal moment equations, we can determine the moments developed at the ends of each member. After we obtain the internal moments, we may proceed with determining the support reaction using equilibrium equation for each member. You may try and work it out. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.